It's my ple it's my pleasure to introduce Al Weimer. So Al is the Clark Professor of Chemical and Biological Engineering at the University of Colorado Boulder. That's where I did my graduate studies, so I'm especially pleased to have Al here speaking today. So Al joined the faculty at CU in 1996 after a 16-year career including the 2015 AICHE Nanoscale Science and Engineering Forum Award and the 2017 AICHE Lifetime Achievement Award for Particle Technology. Al is a co-founder of ALD Nanosolutions, which recently merged with Forge Nano. He's a recipient of the Dow Chemical Company Excellence in Science Award for the invention of commercialization of advanced oxide materials. He holds 40 issued patents, has directed the research of 34 PhD students and published 225 peer-reviewed research articles. He's also an Inventor of the Year at both CU and Dow. He's a fellow of AICHE and was inducted into the National Academy of Inventors in 2018. So Al, thank you for coming today to give this seminar. We're looking forward to it. Go ahead.
Yeah, thanks, Matthias. I appreciate the introduction. So yeah, welcome from the University of Colorado in Boulder. And what I'm going to talk about today is some work that we have done recently. Actually, Jinhua, who's on this call, also had a role in this with testing these particular materials at MUST. So basically, an improved understanding of the role of ultra-thin ALD films on lithium metal oxide cathode materials. So one thing that I want to point out here is that ALD is actually a very significant process. People tend to think it is very expensive, and I'm going to show you that it actually isn't. But one of the key aspects here is that Dr. Santola received the Millennium Technology Prize in 2018 for inventing this technology, and that doesn't happen unless the technology clearly has some substantial applications. And I list some of those here. Rika Pruinen was involved in that particular nomination, and I wrote some supporting letters also for that. So for those of you who may not be familiar with ALD, let me just go through a very simple schematic. Basically what you're going to do, I'm going to show you the example of depositing aluminum oxide on a surface. Alumina can be deposited through a CVD reaction, a binary reaction involving trimethyl aluminum and water vapor. The byproduct is methane. But typically what we do for atomic layer deposition is we carry out the reaction on the surface using functional groups. And the key is to avoid the presence of the two gaseous precursors at the same time. So you really want to avoid chemical vapor deposition. So here we start out with hydroxyl groups on that particular surface. Typically it could be just by exposure of humidity in the air. We bring in TMA, we form, we take those hydroxyl groups, convert them to methyl groups. We convert them all, and then we sweep out if there's any remaining methane. We now have a methylated surface. We bring in water vapor and convert those methyl groups back to hydroxyl groups, and in that process put down a submonolayer of aluminum oxide and then repeat that process. Now the key to the process in order to achieve low cost is to not waste any of the expensive precursors. So in this case, it will be not wasting trimethyl aluminum in coating these particles. I'm going to talk a little bit about that later, but that is one of the key aspects here, is if you can very efficiently utilize the chemicals. Okay, so the growth is very linear and conformal. This is some work that was originally done in Steve George's lab, and what you see is a film placed on a silicon wafer, a flat silicon wafer, and after 3,000 AB cycles, the film thickness is 3,860 angstroms, and the roughness is only 4 angstroms. So basically, you can lay down a very uniform film, and you can control the growth rate, or you can control the thickness through a very uniform growth rate. In this case, like 1.29 angstroms per cycle. Now, you might ask, like, why would anybody actually do this? And with those many cycles, right? And that was done basically to prove the point that, in fact, you could lay down nearly uniform pinhole-free films, nearly perfect with very little roughness. There's a substantial amount of interest in coating particles by atomic layer deposition. This is up through 2018, but you can see sort of like an exponential increase in citations. And this is now close to 5,000 citations per year and around 30,000 citations total. If you go to the Web of Science, Google Scholar will have more, but the Web of Science, if you look up the words in parentheses, atomic layer deposition and in particle, you'll end up with these particular citations. So clearly the interest level in this field is growing and is of high interest. And my opinion is that the applications are probably not yet discovered. There's a lot of opportunity out there to figure out how you can use ALD coating on particles for certain to obtain certain performance. So here's an example of some early work back in 2002, John Ferguson. And what you see here, this is magnified maybe 750,000 times. You're seeing zirconium oxide, and the lines here, basically the atomic structure, zirconium, oxygen. But what is particularly impressive is that each individual primary particle of zirconia is coated with a 25 angstrom film of boron nitride without gluing the particles together. And so the fact that you could place these nearly uniform, these uniform near perfect films on individual primary particles without gluing the particles together was truly a phenomenal breakthrough that took a long time to be understood. And in fact, I can tell you that we originally did some of this work in the late 90s. And then I presented a paper in 2006 at an IFPRI conference in Santa Barbara. And I was just totally blasted. Like, people were saying, that's impossible. Like, there's no way, because of van der Waals forces, there is no way that you can coat primary particles. And this was like 8 years after some of the original work was done. There was still a lot of confusion and a lot of misunderstanding. And the original 3 proposals that were submitted to the National Science Foundation were rejected because the reviewers came back and said, well, this guy's blowing smoke. That's impossible. There's no way you can coat those primary particles. And it wasn't until 3 years later that we ended up getting a small grant from NSF, sort of like as a discovery research grant. One of the reasons that you can do this is a phenomenon known as what we've termed as dynamic aggregation. So basically you do this in a fluidized bed reactor, and particles, nanoparticles, this is actually fumed silica, nanoparticles will fluidize as larger aggregates. And so what you see here is a larger aggregate fluidized. Typically, they will stay in the bed on the order of 500 microns or several millimeters. But then as these aggregates interact with other aggregates, they tend to shed particles. And so as those particles move from aggregate to aggregate, you end up exposing surfaces, and then that allows you to end up coating primary particles. So these are the OX50 particles after the coating. And they're all exactly the same. After 50 TMA water cycles, the average film thickness here is 5.2 nanometers on every primary particle, and again, without gluing them together. So as I mentioned, this is typically done in fluidized beds. So what you can imagine is you have 2 reactant precursors. So here's trimethyl aluminum and water vapor. You may fluidize the particles with inert gas and nitrogen. Then you bring in the TMA as reactant A. You functionalize those surfaces, methyl groups. You then remove any TMA with the inert nitrogen, any TMA that's left. You then bring in the water vapor. You convert all those surfaces back to hydroxyl groups, and in that process, you lay down 1 sub-monolayer of alumina. And then you repeat that process, basically the A reactant and the B reactant as many times as you want to grow the particles on the particles inside of the fluidized bed. And you can follow the surface chemistry downstream using an inline mass spectrometer. So basically, in the case of laying down aluminum oxide, you're looking for methane as the byproduct. Methane is a byproduct of both the A and the B reaction. So if we take a look at that mass spectrometer signal downstream, what you can see here, if I look at the first dose here being the TMA dose, where I have hydroxyl groups on a surface. I bring in TMA. I convert those hydroxyl groups to methyl groups, and my byproduct is methane. So downstream, I'm looking for methane. So the dose starts right here. The red is TMA. Note that this is a log scale. The TMA is in the noise. You're not seeing any TMA. You start the dose and you start to see methane being generated. Note that it's not until methane drops off that all those surface functional sites are converted, that all of a sudden you see TMA breakthrough out of that system. And so what this tells you is that it's possible to essentially not waste any TMA, be able to coat all those surfaces with TMA, convert those hydroxyl groups to methyl groups. And if you know the amount of surface area in the reactor and you know your gas flow rates, you can determine exactly when to shut off that stream and prevent the loss of TMA, which is very expensive. It's on the order of something like $350 per kilogram. Notice that the B reaction is also it's also the same. You're not going to waste any water. You start the water reaction, you form methane again, and it's not until the methane drops off that you see water breakthrough. So basically, this is the reason why particle ALD is in fact a low-cost process for placing films on particles. You're still going to pay for precursor for very high surface area materials. You still have to coat those surfaces. And so there still may be a lot of gas being used, but you can near effectively use 100% of that gas and not waste anything. So this really opens up the door, say, compared to chemical vapor deposition, where you may be able to get away with very expensive precursors in order to lay down those films. So in order to commercialize particle ALD, there were really two major hurdles that we had to overcome. One was what I had mentioned before, that in general, people did not believe that you could coat primary particles. You were going to agglomerate the particles and you weren't going to be able to coat each individual particle separately. Luis Hakim, who was a student in the mid 2010 area, published a couple papers where he did some substantial characterization and demonstrated that in fact you could coat all the surfaces without agglomerating the particles. And for that work, Luis received the best particle ALD or the best PhD award in the Particle Technology Forum at AICHE. He has since gone off the deep end and he's now a financial guy at Deloitte, I think in New Haven, Connecticut. But he did some pretty fantastic research when he was with us. The second hurdle that had to be overcome in order to adopt this particular technology commercially was the cost, because everybody thought ALD is expensive. And it is expensive if you're coating a flat substrate. So like, for example, a semiconductor substrate, you essentially stick a lot of flat surfaces inside of a furnace. You do ALD, and it's possible because of the fact that you don't have much surface area that you will end up wasting a lot of gas that will not come in contact with those surfaces, and it'll cost a lot of money for the precursor. But what you can imagine is that you could scale up fluidized bed reactors to be very, very large. You can have maybe millions of square meters of surface area inside the fluid bed, and compared to the surface area of the walls in the gas distributor, that's like almost nothing compared to the surface area of the particles. And so it's possible to coat all of those particles, all those primary particles, without wasting any gas, essentially having a mass spectrometer downstream and following that surface chemistry reaction. So particle ALD is low cost. Coating flats could be expensive. So in the case of lithium-ion batteries, and I have to warn you up front, I am not an electrochemist or an electrochemical expert by any means, right? So I don't really do research in the battery applications themselves, more focused in the atomic layer deposition for modifying surfaces. And what was really interesting is this first paper published in 2010 out of the Steve George group. This was a collaboration between the University of Colorado, NREL, and ALD Nanosolutions. And what they showed was that they could put an ALD film with only 2 cycles of ALD, and they could achieve some pretty substantial performance with lithium cobalt oxide compared to the bare lithium cobalt oxide. You can see the deactivation with the charge discharge cycles. You can also see that for 2 cycles, the specific charge density initially is almost the same as with the bare lithium cobalt oxide. If you put down 6 cycles of ALD, it still performed better than having nothing there, but it was not as good as 2 cycles. If you put down 10 cycles of ALD, you basically insulated the cathode particles and essentially killed the performance. So this was really a significant finding. This was the first paper that was published showing the effect of atomic layer deposition films on the performance of these battery materials. And what you can see here is that for 2 ALD cycles, we retain about 89% of the capacity, about 45% retention after the 120 cycles for the bare lithium cobalt oxide. The initial capacity decreases for 6 to 10 ALD cycles. And as I mentioned, 10 ALD cycles is an insulating layer and kills the battery performance. So for me, what was really intriguing for me is why does 2 ALD cycles, like almost nothing, why does that have such of a substantial benefit on the performance of these materials, right? So I guess you could say intellectual curiosity. And the reason that I was really curious about this was the fact that people were always saying that you have these uniform films and the lithium is diffusing through the film because the film's so thin. We'll talk about that here in a second. So this is lithium cobalt oxide from 2010. This is a result presented by BASF in France in January of 2019 in Strasbourg at a battery conference. And what they show is that you can also get, again, ALD provides superior performance compared to dry coating and wet coating and the base material uncoated for NCM 622. So not just the lithium cobalt oxide, but also for battery substrates that are of much more interest today. Essentially, some of the conventional assertions that the ALD stabilizes the cathode defects, inhibits the solid electrolyte SEI layer, protecting the transition metals like nickel from dissolution. The film also scavenges HF, improving lifetime. Essentially, that thin film of ALD has a substantial beneficial impact on the performance of those particular batteries. And generally, less than 6 ALD cycles is preferred for commercial interest. And the reason for that is the cost performance benefit. And typically, as I showed originally, you're going to lay down a film that might be on the order of 1 to 2 angstroms per cycle. And so if you're looking at less than 6 ALD cycles, you're typically looking at films, assuming that these films were uniform, that are less than 1 nanometer. And so the question is, why does this work? How is it possible that such thin films will provide such substantial improvement in performance? So looking through the literature, what you find is that it was theorized that ALD surface coatings provide a uniform film. I showed how uniform those films were on the flats and how we could control the film thickness. Basically, the theory was that a uniform film protects the surface from the side reactions for metal dissolution and the phase transitions, and that the film is thin enough that the lithium is able to diffuse through the film. So basically, you have uniform films, uniformly thick aluminum oxide films, and a lithium diffuses through. Now, from my perspective with a background in atomic layer deposition, I was not aware of really any system where you put down 2-4 cycles and you have a uniform film because of nucleation, okay? So my take on this was that I see all these papers, and all these papers are basically saying that these films are so thin and perfect that the lithium diffuses through the aluminum oxide, and that allows you to for that battery to perform that lithium movement. And I I didn't really buy that. And looking at some of the models that have been developed for ALD growth, this is some work from Craig Parsons at NC State. What you can see is that, in fact, you have nucleation. Those films tend to grow, right? So basically, there's modeling up front. Rika Puranen, this paper's now been cited probably about 1,500 times. This is like the Bible of alumina ALD growth. And what Rika says is that the first ALD reaction cycle occurs on the surface of the original substrate material. The following cycles are usually on a surface with both the original substrate and the ALD grown material exposed. And after several ALD cycles, the exact number depending upon the growth rate and the growth mode, finally on a surface with only the ALD grown material. So to me, it was, you know, the suggestion is that you have semi-continuous, non-uniform film growth. That's what we had always seen. And so I was really confused by the fact that I read all these papers with ALD on these cathode particles, and people are talking about uniformly thick films, which ALD is known for, but so thin that the lithium diffuses through. And so here's a study, John Ferguson again back in 2002. Here we're looking at in situ FTIR, and we're looking at the coating of aluminum oxide on boron nitride. And what John shows is that it takes about 8 AB cycles, about 8 ALD cycles, until you actually have alumina over the entire boron nitride particle. And I could show you the same thing for like iron particles that are coated as well. And so basically you're looking here at a larger number of cycles. And so my question was, how can 2 cycles or 4 cycles provide this uniform film, particularly when you have mixed transition metals like nickel, manganese, cobalt with lithium on some of these. And so the hypothesis for this was that for less than maybe 6 ALD cycles, and again, I say 6 ALD cycles because commercially you're interested in the fewest number of cycles in order to have the best cost performance benefit. So my hypothesis was that the film coating is actually non-uniform and non-uniformly thick. And somehow you're able to stabilize the transition metal oxides in the presence of the electrolyte without blocking the lithium intercalation pathways. That basically somehow non-uniformity within this deposition process and nucleation promotes lithium diffusion, okay? So how do we study that? How do we investigate film uniformity, non-uniformity in the angstrom length scale? So if we take a look at different methods for studying the surface, everybody does XPS. And the resolution of XPS is about 5 nanometer. But you have to remember, we're looking at films that are typically sub 1 nanometer. And so the 2 methods that will allow you to gain information in that space would be low energy ionization spectroscopy, which is looking at the first outer atomic layer, and TOF SIMS, which has a resolution of about 1 nanometer. So for up to 6 ALD cycles, we need a resolution at the surface less than 1 nanometer. So our objective was to use low energy ionization spectroscopy and TOF SIMS combined in order to have a better understanding of what is happening on the surface. So low energy ionization spectroscopy looks at the first atomic layer. It's quantitative, but it can't measure lithium. On the other hand, TOF SIMS has a resolution of 1 nanometer. It's qualitative, but it can measure lithium. So let's take a look at how we can use these 2 methods in order to study the coating of an ALD film, particularly of aluminum oxide, on the surface of an NMC111 material. So we used NMC111 as a base material. Obviously of interest today, we're interested in 811, high nickel cathode materials. But here we didn't want to be tied into any particular company. So we went to Fisher Scientific, bought some pretty low cost NMC111, carried out alumina ALD 2, 4, 6, 8, 10, and 12 and 15 cycles. We removed samples. We did not do separate batches in order to make sure there wasn't any kind of error associated with different batches in the fluidized bed. We did elemental analysis and high resolution spectroscopy to understand the deposition and nature of the films. Xinhua actually took these and made electrodes from them, studied these in coin cells up to 250 cycles. And what he showed was that, and what we were expecting, was that 4 alumina ALD cycles provided the best performance. EDS also showed apparent uniform aluminum distribution across a population of particles. This was key. There were no uncoated particles detected, for example, 2-4 cycles. We used a vibrating fluidized bed reactor, as I had mentioned, following the surface chemistry downstream with a mass spectrometer. So if we take a look at those samples using low energy ionization spectroscopy, what we see here on the left, and what I show as I move up here, the cycle number 2, 4, 6, 8, 10, 12, 15, what you can see is we can see the growth of an aluminum containing layer. So I'm going to say, okay, maybe that's aluminum oxide, which is what you expect from TMA and water. It's clearly visible with an increasing ALD cycle. So obviously we are depositing aluminum on those particles, and as we increase the number of cycles, we're seeing more and more aluminum. In terms of the cobalt and nickel, what we see is that the presence of manganese, cobalt, and nickel are in fact at the surface. They're completely suppressed. So here we're going down with cycles, and they are completely suppressed for about the 10th ALD cycle. So essentially, aluminum is being deposited, and it looks like it's being deposited on the transition metals, manganese, cobalt, and nickel. But remember, we can't really detect lithium. So if we integrate these spectra, and what you see on the left here is the fraction of nickel, manganese, and cobalt covered by alumina, and on the right, the fraction of alumina coverage. And so the way to interpret this is that we are assuming that at 15 cycles, our assumption is that we have total aluminum oxide cover. That's an assumption. And we're also, when we make this comparison of the percent covered, and when we're looking at it relative to the manganese, cobalt, and nickel, that percent covered is relative to the initial amount of manganese, cobalt, and nickel. So the normalization is such that the aluminum data normalized to the sample cutter with 15 cycles, since represents the maximum amount of aluminum deposited within this study, and the manganese, cobalt, and nickel were normalized to the manganese, cobalt, and nickel signals of the uncoated sample to determine the fraction of the original manganese, cobalt, and nickel surface atoms that were covered over the course of the deposition. And what you see here is that between 4 and 8 cycles, it looks like about 80% of the manganese, cobalt, and nickel happens to be covered, but the surface contains only about 40% of the ultimate aluminum coverage. So this is pretty interesting. But you got to remember, right, what's missing there is lithium. From 10 to 15 ALD cycles, the manganese, cobalt, and nickel are nearly to completely covered, but the aluminum signal is still increasing. So as we increase the number of ALD cycles, it looks like we've covered the transition metals. However, the aluminum signal is still increasing, indicating that there's a component of the original surface that is still present that is not completely covered by aluminum. And so the question is, okay, what is that? Well, it must be lithium, except that we can't definitively say that because we can't measure lithium, right? We suspect that the missing component is lithium, since low energy ionization spectroscopy can't detect lithium. So then we go to TOF SIMS. So now we look at 0, 4, and 15 cycles of ALD. We're looking at lithium, nickel, manganese, cobalt, and aluminum. And what you see here initially is that the nickel, manganese, and cobalt all appear to be suppressed at 15 ALD cycles. We're basically covering up the nickel, manganese, and cobalt. The aluminum obviously is present, and we are seeing an increase. The aluminum containing film is clearly visible and growing. However, we see that lithium is actually still present on the surface after 15 ALD cycles. So this is actually the first study that showed that lithium is still present after you carry out atomic layer deposition with aluminum oxide on the surface of those NMC cathode particles. So if we look at the absolute signal counts from the top SIMS map, remember that the resolution is 1 nanometer. What we see here is that the growth of the aluminum begins to level off at about 4 to 15 cycles. So we see the manganese, nickel, and cobalt being covered. The aluminum appears to level off. And we also see lithium decreasing. However, and again, cobalt, nickel, and manganese highly suppressed between 4 and 15 cycles. But significant lithium is still present on the surface. 26.9% of the lithium still present on the surface after 15 ALD cycles. And if you look at this, and you look at free energy minimization calculations, lithium hydroxide, which is used typically in the synthesis of NMC materials, reacts with aluminum oxide, and the stable product is lithium aluminum oxide. Okay, so we're suspecting that obviously we've got lithium and aluminum on the surface, oxygen's present. We have lithium aluminum oxide on the surface, and somehow with the ALD process, there's been an environment created that appears to preferentially coat and protect the transition metals while allowing lithium to move to the surface. So lithium is mobile, and it appears to still be on the surface of those particles. So the next thing we did to try and also understand this is we went and we acquired lithium hydroxide and lithium carbonate, and we carried out the same ALD that we did on the NMC 111 materials. And what you'll notice here is that for lithium carbonate, it appears to grow by atomic layer deposition. In other words, there appears to be a uniform film growth and it goes through zero. However, for lithium hydroxide, there appears to be a substantial demarcation at zero. And what this would appear to indicate is that there must be some non-ALD stoichiometric reaction that's occurring between lithium hydroxide and TMA water, or lithium hydroxide and aluminum oxide. And if you go look at FactSage, the free energy minimization product is lithium aluminum oxide. And so we suspect that what's happening is that with any lithium hydroxide present on the surface, which in general is going to be the case when lithium hydroxide is used as along with carbonate, is used to synthesize these particular cathode materials, that is going to stoichiometrically react, and you're going to form lithium aluminum oxide. But then, you know, if you continue to do ALD cycles, you may still insulate that system because you're still going to eventually put aluminum oxide on top of the lithium aluminum oxide. So by looking at both of these results, our conclusion is that the ALD films cannot be chemically uniform or uniformly thick for less than 6 ALD cycles. And the takeaway for the as-produced ALD-coated CAM materials, again, the general theorization up through about 2019 on every paper was essentially that you put down a uniform film less than 2 nanometers of alumina, and essentially that film is thin enough that lithium can move through that film and do its thing. What we've shown here in this work is that in fact, those films are non-uniform, they're non-uniformly thick, and the outside is really a combination of lithium aluminum oxide and aluminum oxide. And if you'd like to learn more about this, you can take a look at this paper that was published in October of 2019, about a year ago, by Amanda Hoskins in ACS Applied Nano Materials, which goes through these slides that I've shown here in a lot of detail. The last thing I wanted to mention here was sort of on the application. So this is now a spatial continuous particle ALD reactor. This is a silhouette of a person, so you can see the size of this. And basically, this particular process is able to process about 3 metric tons a day of CAM materials with the film. And ALD Nanosolutions delivered this as the first commercial reactor to a battery materials factory. This was published in their 2019 first issue, and it went to BASF. BASF presented this picture again in Strasbourg, France in January of 2019. So basically in this process, instead of using a fluidized bed, the particles essentially move by vibration through this particular system, and you carry out any number of cycles that you want. So it could be 4 cycles or 6, and essentially what you're doing is you're spacing the A and B and the inert flow intermittently along the course of that particle path. In January of 2020, ALD Nanosolutions and Forge Nano merged. Prior to that, they were competing with each other. And this entity, which is actually a spinoff of CU about 20 years into it, is supported by a number of strategic companies, including Volkswagen, LG Chem, Mitsui Metals, Sumitomo, an investment company, and I think Air Liquide is also now an investor. Here is an example of a particle ALD reactor at CU. So we currently do research CFD modeling to understand how to improve the performance of that particular system. To give you an idea of some of the things I do in my research lab, we are a very applied lab. Maybe that comes from my industrial background, probably. We carry out particle ALD on a number of different types of surfaces. We have different applications. We do high temperature chemical reaction engineering up to 2000 degrees C or even higher. We license FACSAGE for some of the thermo calculations. We carry out solar thermal processing. In particular, we're interested in the splitting of water and carbon dioxide using concentrated sunlight. We are currently doing research in developing electric reactors. In general, I believe that renewable electricity is going to be prevalent. And instead of burning natural gas, use electricity and figure out how to optimize the use of electricity in carrying out such reactions. We do additive manufacturing. In particular for ceramics, we do direct ink writing using core shell particles that might be prepared by atomic layer deposition prior to making these gels. We also do a lot of applied particle ALD catalysis research. We've done some work in hydrogen fuel cells. In fact, some of you may have remembered Wilson McNeary, who was one of your students a number of years ago. Wilson was an NSF fellow, came to work with me, and has published, I think, 5 papers from our group in the fuel cell space. He's currently a postdoc at NREL. We're also looking at reverse water gas shift, chemical vapor deposition, gas to liquid technology, and catalyst stability by putting films on the outside of catalyst particles. We're looking at CO2 capture and release using ALD functionalized support materials. Particle processing, as I mentioned, continuous spatial particle ALD. We do a lot of CFD modeling of certain types of chemical reactors that we're interested in. We have some work in a nuclear area, putting down corrosion resistant barriers for hydrogen, and also looking at some solar thermal applications with some barrier films. We have recently gotten into hypersonics, which is being led by our aerospace department, and we're looking at high temperature materials for IR transparency, thermal shock resistance for making the structure of some of those aircraft. We look at phase change materials. We're interested in silicon metal and high temperature kinetics. This is some of the equipment that we have in the lab for doing some of these. We have a high temperature TGA integrated with the mass spec, a pretty large moving bed reactor, high temperature, again, a CM furnace. We have 4 of these particle ALD systems, direct ink writer. We have a high temperature 2400 C graphite transport reactor. We can also use that for sintering. We have a very, very nice world-class high flux solar simulator for carrying out concentrated sunlight to drive reactions. If we want to study that chemistry using electric furnaces, we have stagnation flow reactors here. This is actually a beautiful site. I was away at a meeting and I asked my graduate student, are the stagnation flow reactors running? And about 15 minutes later, he sent me this picture. He says, yeah, look at that. They're both running. It's a beautiful sight in the lab. We have a fuel cell test stand and also a half cell rotating disc electrode. We have a dilatometer to study the effects of densification, sintering kinetics, particularly for ceramics, to begin our continuous particle ALD process, spatial. A number of supporting pieces of equipment. Our latest item is actually a Perkin-Elmer ICP. We get a lot of use out of this, and we have our own CEM microwave digester to go with that in order to make sure we get good results from that particular ICP. These are my current students and some of the things that they do. Haley came to us from Georgia Tech. She's doing the CO2 capture. Megan's looking at ALD catalysis, electric reactors. Julia is looking at the spatial particle ALD, gauge CVD reactors using ALD catalysts for growing carbon nanofibers. Becky is looking at the ALD ceramics, the direct ink writing, and also flash sintering. We collaborate with a mechanical engineering professor. Sarah is studying the nuclear energy application films. Justin is looking at isothermal water and CO2 splitting. And my postdoc, Kent Warren, is in the solar thermal reaction engineering group. So with that, I can give this nice talk, but the people that do the work are shown here. The graduate students, they've been very prolific. This is Wilson, so you may remember him from his days at Mizzou. And the students have all done a fantastic job. We have 100% placement of all of our PhD students. And with that, I'm happy to try and answer any questions that you might have.
Great, thank you so much, Al. If you have any questions, feel free to post them in the chat. You can unmute yourself if you'd like. We have a couple questions already, Al. The first one, approximately how long is a single cycle for the fluidized bed reactor?
So it really depends upon the surface area of the particles that you have in there and the gas flow rates. And so it could be as short as seconds, or it could be as long as hours. It really depends upon the surface area and also some of the chemistry. But typically the TMA water is very fast, and surface area will dictate that.
Okay, thank you. The next question here, can photoemission spectroscopy with energy less than 90 EV be used to study the sub-nano films?
I don't know.
Okay.
Sorry.
That's all right. Yeah. Any other questions? So I have one. So I'm curious, there's been some recent work about carbonates on the surface of these battery materials, kind of as synthesized or in the storage conditions, carbonates can form on the surface. And there's been some work examining reactions of ALD precursors with those carbonates. I guess I'm curious, to what extent does any of your data that you looked at show some evidence of carbonate on the surface of the NMC to begin with, kind of in the as synthesized form or as received?
Yeah, so some of the XPS showed that there would be carbonates on the surface, but I don't, my experience and my understanding is that carbonates are not really beneficial. So one of the things we showed from this work was that the carbonates will be coated with aluminum oxide very effectively. So they get coated just like those transition metals. The lithium hydroxide appears to be the active material that allows the lithium to move. And so it would appear that the ability to control lithium hydroxide or lithium on that surface prior to doing the ALD is really pretty significant.
Okay, so you did see evidence of the lithium hydroxide as well then, it sounds like?
You can't see the hydroxide with XPS. So we tried to do NMR work. We were not able to see hydroxide, but we suspect that was there.
Okay. We have one more question in the chat. I am curious why the use of ALD for lithium battery cathode coatings. What is the benefit of of AL203 compared to other metal oxides such as titanium oxide, zirconium oxide, et cetera?
So people have done work with all of those. And again, my understanding is that the lithium aluminum oxide that forms is amorphous and allows the lithium to diffuse through. I think there is also some effect with reacting and containing HF, which may be formed from the electrolyte. So it's not, so, you know, zirconia, titania, other films have been used, but I don't believe that they have had the same type of performance as aluminum oxide. But let me also say that the real key here moving forward is 811. And 811 is going to behave much differently than the 111, even the 622, I believe. And so the ability to utilize like NMC 811 would be very significant. And I would say that that little company, you know, Forge Nano, their key drive has to be to get 811 to work. If they can get that to work, I think they're going to see a pretty good business, because the competition is not as good. Like if you looked at those results I showed with BASF, the dry coating and the liquid coating were not as good. That you clearly can't control the film thickness, and ALD is really the preferred process, and it's lower cost. But just like, you know, like anytime you work with car companies, they're looking at pennies, and it's very difficult to have somebody change the way they're doing things. And so right now, that's you know, that's the real key, is that the car companies have to be motivated to go to ALD. And when that happens, I think you'll see a lot more emphasis commercially with those particular systems. And in showing the spatial ALD, it's possible to process, you know, Forge Nano has designs out to process, you know, 30 metric tons of CAM materials per day. That with that system is pretty significant.
Thank you. We have another question. Can you talk a little more about how the particles were agitated or unagglomerated during the coating?
Yeah, so, you know, there are various ways that you can agitate the particles. I show a fluidized bed reactor where you're using drag forces above the minimum fluidization velocity. If you have real sticky materials, you know, you can use mechanical vibration, at least in a small scale system in the lab that works well. I showed a stir. People aren't typically going to use a stir in a larger system. You can also pulse the gas flow. So it's possible to pulse the gas flow, and again, to be able to promote agitation of those particles. And again, I think the key of why you're coating primary particles instead of aggregates, two things there. One is the dynamic aggregation that I talked about, where you have aggregates of particles that are lightly aggregated, and as those particles move beside each other, they shed. And particles from one aggregate move to another, exposing surfaces. The other thing is that the ALD reactions generate gas. And so you can imagine that you're carrying on ALD and you have two particles next to each other. They're generating gas, and it's kind of pushing them apart. And so you have two different dynamics going on that promote the coating of individual primary particles.
Thank you. So I think we could take one or two more questions if there are any. We're getting close to the end of the time here, though.
I'll ask a question.
Yeah, go ahead.
Yeah, I was just wondering about the nucleation on the surface. Do we talk about nucleation of the water vapor nucleation, or we're talking about the TMA? So
really, it's the nucleation of the aluminum oxide.
Okay.
And so, you know, you're depositing on the surface, and you're not going to get, you know, there are going to be issues there where you have ligands and things, and you're not going to actually coat every site. And so it takes a number of cycles in order to coat. And that's why I was really intrigued by this, because I read all these papers, and people are talking about, they're showing like a 2-4 cycles works. And then they're saying, well, these films are uniform, but they're so thin that lithium diffuses through them. And my take was that I couldn't believe that the films were actually uniformly thick. In fact, there was even a patent out there where somebody was claiming that. And so, you know, the real question is, how do you look at that? I mean, and the combination of lice and TOF SIMS was significant. Let me also say that when we did this, we had to send the samples to Germany to do the low energy ionization spectroscopy, and the TOF SIMS was done with EAG in Minneapolis. And they were fairly expensive to do all of that. Today, at CU, we actually have our own low energy ionization spectroscopy system, and the Colorado School of Mines has the TOF SIMS. So I guess the other point I want to make is the combination of those two analytical techniques. You know, using those two together really allows you to take a hard look at the surface, even at something where you're only putting down, you know, like a few angstroms. And so I think that is really pretty significant compared to XPS. Like XPS is the old standby, but when you have films that are this thin, you know, an XPS isn't going to work with particles, you know, anyway, if you do depth profiling, because you're always going to see the outer edges.
Thank you, Al. I really thought that work was impressive with those that combination of techniques. That was really neat. I think unless there are any other questions, I think it's time to wrap up.
So if I can ask you, keep sending your best students. So maybe some of you remember Julie Nguyen, right? She graduated last year from Missouri, and she's currently in my lab doing independent study, and she will be the student who is doing our 811 research.
Yeah.
So she was working with Brett Allery. I think Brett probably is on there, but anyway.
Well, I see him on there, yeah. So anyway, Julie is working with me right now, and also with Hendrik Hines doing some MD modeling of that particular system. And yeah, she's truly a very nice person, and she's gonna be a fantastic student, just like Wilson McNeary was. Yeah. So keep sending your undergrads out there and let me know when you do it.
And Sam Hoff also is there. I hope he's doing fine.
Okay. Yep.
Yeah, he's not working with you, but somebody else, I guess.
The students love going out there. I think the mountains and the weather are a big pull. Not to mention the excellent researchers. Yeah, the excellent researchers as well. All right. Well, thank you again, Al, for giving this talk today. I wanted to mention everyone, the next seminar it's a couple weeks away. It is on October 13th. It's Taylor Vole from the University of Maryland. I posted in the chat the link to that seminar schedule for those that are interested. And again, thank you, Al. It was a wonderful talk.
Great.
Thank you, Al.
Bye.
Thank you, Al.